Okay, good afternoon. Today we'll begin FETs. We'll spend about a lecture and a half on semiconductor fundamentals of FETs and how the devices work, which, by the way, is a whole big topic that can take an entire quarter. And so we're just going to skim the surface, so to speak. And then from next week onwards, not quite Monday, but next Wednesday onward, we'll look at applications of FETs in their circuits. Okay, so far we have looked at BJTs, diodes and BJTs, and in like a BJT, an FET is also a three-terminal device, and the terminology is also kind of very similar. So in a BJT, we have a collector, a base, and an emitter. And in an FET, we have the drain, the gate, and the source, kind of analogous. Collector and a drain, emitter and the source, and base and the gate. The idea of three-terminal devices, or the principle, is pretty much the same. We have two terminals, current flows between those two terminals, and the third terminal in the middle is going to control the flow of that current. So it's the same in an FET. Now, FETs stand for field effect transistors. Unlike a BJT, FETs are symmetrical by their design and their construction. Their application does not always mean that they're going to be symmetrical devices, but the physical construction is actually symmetrical. Now, BJTs, we saw some applications where primary usage was as a switch. We operated in a cutoff or saturation region, meaning it's either off or it's on. So it's switching, right? But in order for it to switch, we do require some amount of current to actually go into the transistor. Okay. Well, an FET can be operated as an amplifier and as a switch, but is a far better switching device than the transistor because current does not actually go into the FET. Okay. So it is a better switching device. Okay. Better switching device. The concept of an FET, the theoretical concept, was presented at least 10 years before BJT. But BJT was the first device that was actually presented. A working prototype was first presented. FETs took some time. It was about 10 to 15 years after the presentation of a BJT. It took advancements in fabrication engineering and the semiconductor industry before a working FET could be demonstrated. But the operating principle, the theory, is actually older. The concept of an FET is older than that of the BJT. But the BJT can be said to be a current control device because of the input of the current. FET is known as a voltage controlled device. Okay, voltage controlled device. A quick overview of doped semiconductors. N-type material is created from column 5 elements. P-type material are created from column 3 elements. Column 5 elements have excess of electrons, hence we get excess of electron charge carriers, hence a N-type material. Column 3, we create an excess of holes or positive charge carriers, hence P-type material. They are known as the majority carriers, and in each one of those, we still have intrinsically generated holes and electrons, which are far less in number, hence they are known as the minority carriers. Okay. The implanted impurities in an N-type material are donor atoms, and because they're donating an electron, and because they donate an electron, they're left with one extra positive charge. So they're positively charged ionized donor atoms, and in P-type material, it's negatively charged acceptor atoms. Okay. All right. So FETs there are two kinds of FETs actually. There is a device known as junction FET, JFET, and there's something which is far more common and far more ubiquitous today, which is the MOSFET. Okay, junction FET is JFET, MOS, metal oxide semiconductor is the MOSFET. Now, the metal oxide semiconductor refers to a sandwich material of a metallic layer, an oxide layer, and then a semiconductor layer. Okay, so let's take a look at what it actually is. The oxide refers to, the O refers to oxide, the oxide refers to silicon dioxide, okay, which is actually an insulating material. So silicon dioxide is an excellent thermal as well as electrical insulator. Where have you seen silicon dioxide before? Any guesses? You could be touching one right now. Glass. Glass is silicon dioxide. The smartphones, your laptops, displays, everything has a glass screen on top. That is silicon dioxide. So it's an excellent thermal and electrical insulator. Okay. So the sandwich layer actually is some sort of conducting metal, an insulator, and a semiconductor. I like to call it as conductor, insulator, and semiconductor. CIS or SIC, either ways. So all three of them are in there. You have a conductor, you have an insulator, and you have a semiconductor. And that's what is in pretty much every microchip that we use today. Okay. All right. So here is a side view or a cross-sectional view of a sandwich layer. Okay, you have a semiconductor material, then you have the insulating material. This is very thin, by the way. The thickness is exaggerated. And then insulating material is separating the metallic structure and the semiconductor material. Okay, so this is a P-type material. P-type material has excess of holes indicated by those small circles in there, and the electrons are indicated by the black dots. Electrons, of course, would be far less in number than the number of holes in a P-type material. But what happens if you apply a positive voltage between the metal and the semiconductor? You're now applying an external electric field. The metal is positively charged. Semiconductor would be negative charge. And so what happens? The insulating material is very, very thin. And so it starts attracting all the electrons. It's pulling it up. It pulls all of the electrons up towards the surface of that semiconductor material, which is indicated by these arrows here. So they're being pulled up. And because you're applying a positive charge at the metal, the electric field is going to push the holes away from the surface. So the holes are pushed down, indicated by these red arrows. Okay, so the holes are pushed down, or pushed away from the surface of the semiconductor. Note that we applied an external electric field. It causes an effect inside the device, but no current can flow through. Again, there is an insulating material, so there is no current actually flowing through the device because there's an insulating material that separates it out. What kind of element does this bring to mind? You apply a voltage to two plates separated by an insulator. EE115. You use several of those in the lab. Tiny things. Capacitor. She's the only one who knows or brave enough to speak up. It's a capacitor. So capacitances are a big deal in transistors, especially FETs, MOSFETs. We are, again, not going to spend too much time on it right now. But again, that results in a capacitance, right? So there is a capacitance because of the physical construction of the device itself. You have two conducting plates separated by a insulating material. All right, but everybody with me so far? You apply a positive voltage in a p-type material, pushes the holes away from the surface. Electrons that are there in the minority are pulled up towards the surface. Yes. So we haven't yet. So, okay, the question we asked is about FETs being symmetric. We haven't reached that point yet. So that's the next slide coming up. So where was I? But everybody is so far so good. Positive voltage pushes the holes down. If it was a N-type material, you'd apply a negative voltage, it would push the electrons away from the surface. It would pull the holes up. But the point is, whatever voltage you apply here, depending on the P or N-type material, is going to attract the minority carriers and going to repel the majority carriers. Okay, if it's a P-type material, you apply positive voltage. If it's an N-type material, you apply negative voltage. All right. If that positive voltage increases, then it creates a thin layer of free electrons right here. But the electrons are not in large numbers. Okay, again, it's a minority carrier, so they are not present in large numbers. All of the holes are pushed down. And this region is depleted of holes. It is also known as mode of the depletion region. Okay, so this is the central. This is central to the operating principle of a FET or of a MOSFET. Sorry, okay, MOSFET. All right. Now let's get to the construction of a MOSFET. So that capacitance in the middle region was right here. Metal oxide semiconductor, MOS. Okay. Now, this is a P-type material. You have a oxide layer in the center on top. Again, this is the side view. This is a side view. You have an oxide material on top, and then you have some sort of metal or metallic gate on top. Now, in modern devices, this is not even made out of metal. It is made out of polysilicon. Polysilicon is an amorphous form of silicon, hence the name polysilicon. It is heavily doped polysilicon, so it behaves with metallic properties. Okay, so construction and fabrication is far easier with polysilicon than with pure metal. Anyway, so what do we do then is, in this P-type material, we implant N-type regions on either side. Okay, we implant these N-type regions, and these N-type regions are heavily doped. Okay, so these are heavily doped. These are heavily doped. If this was a N-type body or N-type material, then you would have heavily doped P-type material. So just as a quick, if this was N-type, then we would implant P plus. The plus simply indicates heavily doped, right? P plus. That's not PT, it's just P plus. Okay. So P-type material, you have a heavily implanted N plus, and then you have an insulating material that isolates these two terminals. Again, this is isolating here, no contact whatsoever. And then you have some metal that's in the center. And this metal, this is like, it's important to fabrication and device. It's not important here for our understanding. But this metal kind of should overlap. I'm drawing these lines at an angle. This metal should kind of overlap in that sense, where it affects, where that metal from the top affects each end of that gate. Sorry, not each end of the gate, each end of those N-type materials. Okay. Anyway, so you have the P-type material, you have an N-type material. What happens at the junction? When a P and an N-type material come together, what do we get? A diode. So a diode forms at that junction, and there is a depletion region that is created everywhere. Well, everywhere there is P and N-type material in contact. Okay. And this is an important point to keep in mind. Okay. We have 4 distinct regions in here, physical regions. This big region of P-type material is known as the body or the bulk. Okay, body or the bulk. This region at the top, the metal, is known as the gate. Okay. And then these implanted, this is of course a metal, but the implanted region underneath let me draw it this way. The gray portion is simply the metal that's making contact. That's all it is. But that implanted region are the drain and the source. Okay. Drain and source. And the drain and source, at least as far as this figure goes, are interchangeable. And that is what makes this device symmetrical. Okay. That is what makes this device symmetrical. Now, in real life devices, especially like discrete MOSFETs you buy, and even the chip that we used in the lab, if you noticed, the body of the device was connected to either the drain or the source. If a connection is pre-made, which it typically is, then it is no longer symmetrical. Does that make sense? As shown on the image right now, as shown, the device is symmetrical. But most discrete ones, and especially the chip that we used in the lab, they are not, because the body is connected to either the drain or the source. Yes, go ahead. Clarify that the metal gate is touching the drain. Yes, yes. So it's not touching so much as it's overlapping. So when we apply a voltage to the gate, the effect, the electric field should affect both the drain and the source. Hence, it should overlap. So the gate is small in size. If this gate is small in size, let's say we only have this right here, right? Small gate. It does not overlap the drain and the source, and the effect will not be there. So there will be no channel. There will be a gap left behind right here, and no channel will be established in there. And so there would not be any current flow between the drain and the source. So as I said, it's not an important point in this context right now, but it's a very important point during fabrication and actual operation of the device, that overlap. Okay, all right. So we have, does everybody understand the construction of the MOSFET? Okay, we have a P or an N-type material, and then you have a N or a P-type region, two of them that are implanted at some distance away from each other. And then there is a oxide layer separating the two. And on top of the oxide layer, you have some sort of conducting metal. The channel is created between the drain and the source, and that is shown right here. Channel is shown right here. Okay, this is a P-type device. So what is your guess as to the kind of channel? There's only two options, multiple attempts. Take a shot. You said N, then you change your answer to P. You were right the first time. Because we have two N regions, if we want to connect them, we need a N channel. And so if you have if you have a P-type region that you have N drain and N source, and if you want a channel to connect the N drain and N source, we need an N channel. If it's a N-type material, you have a P source and a P drain, and then you need a P channel to connect them. And from the type of channel, we get N channel MOS or P channel MOS, and thus we have N MOS and P MOS. Okay. All right, so that's the concept. That's the MOSFET concept. Let's go to the physical effects. Okay. The physics of it. All right, so three processes take place. There's accumulation, there's depletion, and then finally there's inversion that is required for creation of the channel. Yes. So we are again looking only at this portion of the device. So this is basically the entire MOSFET, but the primary semiconductor physics or the physical activity is taking place right here. So we're going to explain what happens in the capacitive region where there's metal, there's oxide in the semiconductor. So conductor, insulator, semiconductor. And then we'll see how the channel is created. And then we'll bring it back into the MOSFET right here. Okay. Yes. So this image is excluding the drain and the source. That is correct. Okay. All right. So accumulation, depletion, and inversion in that MOS capacitor. All right. So we have a P-type material. In a P-type material, if you apply a negative voltage is going to attract all of the holes. Well, if it attracts all of the holes, you now have a channel full of holes, right? It's attracting all of the holes right at the surface of that semiconductor device. So you have a pathway. That's a highway built of holes. But it's a highway built of holes, so only holes can traverse through it. Electrons cannot. Okay. Anyway, so right now we're not dealing with the edges. We are simply dealing with the center of the device, MOS capacitor. So we have a lot of holes that are pulled up to the surface. Electrons are pushed away. But now from negative, let's start increasing the polarity of the voltage. The electric field starts reversing. And now the charge at the top is positive instead of negative. And when that happens, the holes are slowly pushed away from the surface. Electrons are starting to come up. So holes are pushed away, electrons are starting to be attracted to the top. Eventually, when the voltage turns positive beyond a certain threshold, all of the electrons that are available are now this is technically not called a channel, but I like to call it a channel. So it's positive holes channel. But again, that channel is useless because it cannot allow conduction pathway for electrons. All right, so now when the voltage crosses a certain threshold, all of the holes or most of the holes are all pushed down and the electrons are pulled up. So now you have a channel of electrons. So your charge is completely inverted from positive to negative, or the channel is now completely made of negative charges versus earlier it was positive charges. And so this region is known as inversion. And this region is known as inversion. So far, so good. All right, so now this is basically a little bit of physics calculation for the surface charge. This is known as phi s. This is the equation phi s max, which obviously is a function of the doping, right? The dosage determines the number of implanted atoms, which is going to determine Na, right? That technically is the number of implanted atoms. And then this voltage right here, the threshold voltage, that is the voltage that is required to invert the channel from positive to negative. Okay, that voltage is similar to a diode voltage drop. Diode voltage drop is required in order for the diode to begin conducting. It's about 0.6 to 0.7 volts. This voltage, the threshold voltage, is typically far smaller. In modern devices, it's far smaller. It's less than half of 0.6. Okay, so close to like 0.3 or so. But again, depending on the design, depending on the fabrication, you can have threshold voltages from like fraction of volts to like multiples. The drain and the source dope the same for the most part? Yes. The doping is the same for the drain and the source. External, yes. Yeah. Yeah. In modern devices, as far as I know, they're still physically designed to be symmetrical, but there are certain fabrication technologies where I read that was, I need to confirm this again though. But for the most part, they're still symmetrical. All right, so let's look at the N-channel MOSFET and the rules of operation. Okay. All right, so we have a P-type body. We need to create a N channel because we have N-type regions on either side. Okay. All right. First things first. The conduction must take place between the drain and the source, right? Horizontally. In this image, it should be horizontal along the x-axis, right? Between the drain and the source. However, there are two PN junctions in there. One is from the drain to the body. The other one is from the source to the body. If we do not apply a bias that keeps those regions off, we'll have conduction going in the y direction on the y-axis between the drain and the body and the drain and the source. So across here and across here, because we have a PN junction. So those PN junctions must be off. They must be reverse bias. Otherwise, the current would flow backwards in here and here. We don't want that. We want the current going between these two. Make sense? The drain and the source are the main terminals. We want the current going between the drain and the source. We don't want it going into the body of the device. And so the first rule, the first point is the body must be reverse biased with respect to the drain and the source. And so you would connect in an N-channel MOSFET or this P-type material, the body must be connected to the most negative supply rail. If all we have is ground available to us, meaning 0 volts, we connect it to 0 volts. Reverse bias. Reverse bias the sucker. Okay. Which the reverse bias or no, it won't damage. You're not applying. So the question being asked is if we reverse bias, would it damage the device? No, we are not applying anything in excess of like, 5 volts, let's say. Modern devices run at even lower threshold voltages, like not threshold voltage, digital logic voltage, 3.3 volts. So very, very small, very small. As long as it's off, that is sufficient. Let's say you're working with power MOSFETs, higher voltages, higher currents, then yeah, you might be able to apply larger reverse biases, but it's not going to damage it, no. However, the positive voltage applied at the gate could damage the insulator because the insulating layer is very thin. Yeah, the insulating layer is very thin. It's a fraction of a micron, typically in nanometers, very, very small. So too much positive voltage for a N-channel MOS and too much negative voltage on a P-channel MOS is going to damage or destroy the oxide layer. Yes. Flip it, yes. Yeah, then it will be positive. Yeah, so the question was about if we use a N-type material, then we would apply the most positive supply in the circuit. Yeah. The point is that those diodes must be reverse biased. The body must be reverse biased with respect to the drain and the source. Okay. All right. The device as it is off because there is no channel. There's no channel that exists between the drain and the source, right? We need to create a channel. So we need to apply a voltage to enhance the conductivity, to enhance and create a channel between the drain and the source. Hence, this is also known as an enhancement mode device. Okay. We need to apply a voltage to enhance and create a channel. Hence, it is known as an enhancement mode device. There are devices where the channel is already present. It's already created from the factory, so to speak. And those devices, a voltage must be applied to turn it off. Those are known as depletion mode devices. Depletion mode. Okay, so you have depletion mode MOSFETs. We also have a device known as a junction FET, JFET. A JFET is also a depletion mode device. It always has a channel ready and available. You apply a voltage on it to actually turn it off. We'll restrict our discussion to enhancement mode MOSFETs, where you apply a voltage to create a channel. Okay, you apply a voltage to create a channel. So go back to this image. What did we see? Sorry, not this one. This one right here. When you have a negative voltage, you have a positive channel. Right? You have a negative voltage, you have a positive channel. Slowly, that negative voltage turns to positive. When it turns to positive, there is a crossover between the holes and the electrons. And during that crossover period, we say it's the depletion region because it's completely depletion mode, because it's completely depleted of all charge carriers. It's somewhere in the middle. Holes are being pushed down and electrons are being pulled up, but somewhere around there, it's completely devoid of all charge. So there's no kind of channel in there, neither positive nor negative. And at some point, the voltage turns large or largely positive. where all of the electrons are now attracted to the surface, and you have a negatively charged channel. And so it's completely inverted. So the point being that there is a level of voltage that must be applied to overcome that threshold. And that voltage is known as the threshold voltage. Okay, threshold voltage is the value that is required to create that channel, which is basically inversion from the P channel to the N channel. Okay. And so the third point is that the applied gate voltage must be larger than the threshold voltage. Okay, it must be larger than the threshold voltage. That's the manufacturing. Yes, absolutely. It's design and fabrication. The physical geometry of the design and the doping profile. That is what decides what the threshold voltage is going to be. All right, so 3 modes of operation. You know, I mean, BJT, we have the 3 modes of operation: active, saturation, and cutoff. We have the same, well, not same, but similar 3 regions. But just to mess with the students, they decided to interchange the terms. At least that's what I used to call them when I was a student. They just decided to mess with us. So I'll come back to this, but I'll just go over here to this chart in this graph, and then we'll come back to those regions. You know how in a BJT we have the active, the cutoff, and the saturation region? Well, here in an FET, this is still known as the active, but more commonly, what do you think this is known as? Saturation region. Because the current has reached a maximum or saturated value. Hence, it is known as the saturation region. This region right here at the bottom is still cut off. Thankfully, we don't have to worry about 2 of those. And the region to the left, which is the region to the left of this dotted line, is known as the linear or triode region. Linear or triode region. Okay. So active or saturation, cut off at the bottom, in the linear region to the left. All right, let's go back and see how our MOS capacitor is going to work for our device. So if the gate voltage we're applying is below the threshold voltage, nothing's going to happen. It's a positive channel. It's a positive channel, meaning there is no connection between the drain and the source. A drain and the source needs negative carriers or electrons in there to connect them. So this is a positive channel. Okay. So it's cut off. Gate source voltage, VGS, is less than the threshold voltage. And then you have the gate drain voltage, which we'll talk about later. Okay. We'll talk about later. Well, later as in just a few seconds. All right. So now VGS is starting to increase. We are increasing it from some negative value or even 0 and turning it positive: 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. And let's say VTN, threshold voltage, is 1 volt. At this point, VGS is just at the threshold voltage or just slightly above the threshold voltage, meaning the inversion process has occurred. It is now complete, and you have a N-type channel which connects both the drain and the source. The N-type drain and the N-type source, they have electrons. And now right at the surface of that semiconductor device, meaning right below the gate area, you have an excess of electrons. There are electrons that are pulled from the body of that substrate. They're pulled from the bulk of the substrate. So there are electrons from there, as well as electrons from the drain and the source. They all intermingle. They form one continuous region between the drain and the source. You all with me so far? Where did I lose you? Still with us? Kind of? Yes. This is for a p-type. Well, it's not p-type. It's a p-type material. The body is p-type, but the channel is n-type. No, it's n-channel MOSFET. N-channel MOSFET. Yeah. Okay. All right. So now you have an n-channel that's connecting the drain and the source. What happens if you apply a voltage between the drain and the source? It will conduct. Yep, absolutely. You have electrons in there. If one end is higher than the other, electrons are going to be attracted to the higher potential. So if drain is connected to positive, electrons are going to flow from the source to the drain. If the source is connected to positive, the electrons are going to flow from the drain to the source. Well, but then it wouldn't be called as a source. It would be called as a drain. Well, that's why it's symmetrical device. Okay, if the physical dimensions are exactly the same and the doping profile is exactly the same, it would be a symmetrical device, completely symmetrical device. But again, in real life, many of the transistors that we buy, whether it's discrete or whether it's integrated on a chip, the body is connected directly to the source or to the drain so that it's kept off. But you get the point. We apply a voltage at the gate to create a channel. That channel connects both the drain and the source. And now if you apply a potential difference, meaning a voltage between the drain and the source, electrons will start flowing in direction of that applied voltage. And so the second condition is the gate to drain voltage must be greater than the threshold voltage VTN. So VGS greater than VTN establishes the channel. And then when the gate to drain voltage is greater than VTN, it allows current to flow between the drain and the source. Okay. So VDS, the drain source voltage, controls the drain current. In this case, the drain current is exactly the same as the source current, IS. Right? In the BJT, collector current was almost equal to the emitter current, but some of it goes to the base. Here, the gate does not conduct any current. You only apply a voltage to control it. No current flows into the FET. Hence, FET is a better switching device than a BJT. Okay. Current can also be controlled by controlling the amount of voltage applied at the gate. Okay, if the voltage is far larger or far greater, the number of electrons available are far greater or smaller. Okay, and so overall current can also be controlled by the gate. What happens when you connect so drain VDS is positive, meaning the drain is positive with reference to the source. Both are N-type materials. Both are N-type. If you apply positive at the drain, electrons are attracted to the drain. So current is flowing in the opposite direction, obviously, but electrons are flowing from the source to the drain via that channel. But at the same time, you're applying a positive potential to an N-type material. So the depletion region starts increasing right here. And eventually, when VGD is less than VTN, the channel is pinched off or it cuts off. And when it cuts off right here, we call that as pinch off. We would expect that no more current would flow through, but that's not really what happens. It pinches off, but there's a small gap that's left behind, and all of the electrons still have a pathway to flow through. So it's pushed through that small gap. So even though the channel is closed, physically, there is still a small gap. And electrons, there's a very high charge density because the same number of electrons keep flowing through there. And the characteristic that we obtain looks something like this. So it's linear right here. It's linear right here. So in this region, it's linear. In this region, it's saturated or active. And it flows at a constant level, and it's a constant current source. The amount of voltage applied at the gate in excess of the threshold voltage is known as overdrive, or the gate overdrive voltage. As a simple or straightforward example, let's say in LT Spice, we have a threshold voltage of 2 volts. We can simulate this easily. If you have a threshold voltage of 2 volts, you apply a gate voltage of 2.8, then the gate overdrive voltage is 0.8, which is what we obtain in the output characteristic. Okay, in the output characteristic. So the output is linear for a while, and then it saturates. Okay, and that's how a MOSFET would work. All right, questions? It's a lot of thinking to be done, a lot of reading to be done. So I was saying the total amount of VGS applied minus the threshold voltage is required for it to just create the channel is the overdrive. In the triode region, it's greater than 0, greater than VDS. In the active or the saturation region, it is, well, VDS is greater than VGS. Okay. All right. Think over it, read about it. And then, well, we'll end class here today. And we'll pick up here again on Monday. Quiz on Monday based on BJT applications and BJT amplifiers. Announcement was posted yesterday. And then there's a small reading assignment for the FET also. All right, I'll bid you a good weekend. I will see you all on Monday.